Hi guys, I'm Marcus S. Allen Jr. Welcome back to SM Academy. Today we'll be discussing dynamics and the course is Gen 255. And our topic on the discussion today is the kinematic of a particle. Basically, we'll look at the rectilinear kinematics and the topics mainly is continuous motion. So both getting into continuous motion or the rectilinear kinematics, let us first look at the aspect of dynamics. So what is dynamics? Dynamics is a branch of mechanics that deal with accelerated motion. So dynamics is a branch of mechanics that deal with accelerated motion. So dynamics deal with accelerated motion. There are two branches of dynamics. We see the two branches are kinematics and another kinetics. So there are two branches of dynamics. First branch is kinematics. The second branch is kinetics. So kinematics it deal with what? It deal with the geometric aspect of motion, where kinetics analyze the forces of motion. Let's read the linear motion, discussing the continuous aspect of motion. So continuous motion. So continuous motion can be categorized into acceleration, velocity, and other position. Our first continuous motion is position. Assuming we have an object like this at the origin of 0, right? And move from here to here at this point. So the distance from this point to this point is the position. So the position is the point of origin to the distance the ball travel is the position. Our next continuous motion characteristic is displacement. Looking at the same diagram, we'll have this as our position, right? This is our ball. So if the position change direction, it becomes what? Displacement. So you change in terms of position. So again, you distance, right? After we reach our position, you change in terms of direction. So how about you in position? So for this, here is our value s, and here is our change in s. So the value of change in s here represents what? The displacement. So it means that the total distance from here to here is, we call it s prime. So to find our displacement, change in s will be equal to s minus s prime minus s, because the total distance minus the initial distance, we already call it initial position. Now look at our next continuous motion, which is velocity. So the velocity is a ratio of the displacement with respect to time. So velocity v is a ratio of the displacement, which is a change in the displacement. We say change in s represents our displacement. As we say, we change in the position represents our displacement with respect to change in time. So at times, if we discuss about instantaneous motion where we have a velocity v is equal to the limit as changing t approach 0 of change in s all over change in t. So if we have a limiting value, approach of value, here we can apply in mathematics, we can apply something called first principle of derivative. So if we apply first principle of derivative, meaning that the velocity V will be equal to what? The derivative of what? The position with respect to the derivative of what? Time. So it means that we call this our equation 1. So our equation 1 velocity V will be equal to the derivative of the position divided by the derivative of the what? The time. And look at our next one. Our next is acceleration. So acceleration is the ratio of the velocity with respect to our time. So the acceleration A is equal to the ratio of the velocity with V divided by our time. So it means that we're finding the average velocity or acceleration. We say acceleration will be equal to the change in V with respect to the change in time. So if we reference the acceleration in terms of instantaneous acceleration, meaning that we will have the acceleration to be equal to the limit as change in t approach 0 of what? Change in v with respect to change in time. Like we said to this side, if we have a limited value of this guy, we can apply first principle of derivative. And me just share you a clue what first principle of derivative is. First principle of derivative says that if we have a function like this, we say f of x to be equal to x, for example. If we want to apply our first principle of derivative, the rule says that we have the limit as what? H approach 0 of f of x plus h minus f of x all divided by h. So if you do the expression, you end up 1, such that the derivative of f is 1, is seen as what? Dx. So is that we will have the acceleration will be the limit at changing t approach 0 of this, meaning that acceleration will be equal to the derivative of what? The velocity divided by the derivative of what? Time. So the acceleration is equal to the derivative of the velocity with respect to the derivative of what? Time. Let's try to compare equation 1 to that of equation 2. Equation 1 says the velocity equal to the derivative of the position divided by the derivative of time, right? And equation 2 says the acceleration is equal to what? The derivative of the velocity with respect to the derivative of what? Time. So we can change the value of v here is what? Ds by what? Dt. So we see v in this case we can put ds by dt. So is that the acceleration A is equal to ds v by dt, right? So the acceleration A now will be equal to, and then we'll see v will represent as what? Ds by dt. So we'll have d multiplied by ds by dt, all divided by dt. So if we multiply, we'll have the acceleration A to be equal to d, and d will give me what? D square s by what? Dt square. So my acceleration also is equal to the second derivative of the what? Position with respect to the derivative of the time in terms of second position. So next, let us see something. Here we have equation 1 has v is equal to what? Ds by dt, right? Here we have equation 1 says v equal to what? Ds by dt. So if you want to make dt is such a, we can cross multiply, right? We'll have v dt is equal to what? ds. Meaning that we'll have dt to be equal to ds by what? V, right? Again, looking at equation 2, we have A is equal to dv by dt. So if we want to make dt the subject again, if we cross multiply, we'll have this by this, we'll have A dt is equal to what? Dv. We'll make dt the subject, so we divide by A. So dt will be equal to what? Dv over A. As you can see, dt equal to what? Ds by v, and dt also equal to what? Dv by what? A. So we can call this equation. We will have equation 1, we'll have equation 2, and here we'll get equation 3. right? It's our major equation. So we'll call this equation what? 4. We'll call this equation 5. Because we realize that dt and dt is the same, so we can equate equation 4 to that of equation 5. See another model. So we can equate equation 4 and that of equation 5. So equation 4 says ds by v is equal to equation 5 say dv by what? A. So if we cross multiply, we'll have a ds is equal to v dv. So we call this our major equation. So we call this equation 6. So this is our major equation. So the ADS is equal to our VDV. ADS equal to VDV is where we relate acceleration, position, and our velocity at the same time. So let's look at certain things we can use called finding the function. If we want to represent the position as a function of time, if you want to represent the position as a function of time, but both going to representing the position as a function of time or the velocity as a function of time, where we realize the acceleration is constant. Let's first climb as our favorite or instantaneous formula. So our first formula we say that v is equal to what? ds by what? dt, right? Is our first formula we say. And our second measure we say a is equal to what? v by dt, right? And our third we say is that a also equal to what? t square s by what? dt square, right? And our third we say is that ADS is equal to V dV, where we relate acceleration, position, and velocity at the same time. So at times, in a case, acceleration here is not constant, right? So let's deal with where we have a constant acceleration. So we have a constant acceleration, meaning that we can have, if the acceleration is constant, let's use a condition. If acceleration is constant, right? Acceleration is constant. When acceleration is constant, meaning that we can have our velocity as a function of our time. So let's look at the first one called the velocity as a function of time. So when we say velocity as a function of time, meaning that we have f of t, right? Such that v is the dependent variable and t is the independent variable. So we'll have velocity as a function of our time. So if we want to derive the equation that says the velocity as a function of time, we can use our first equation that says v is equal to what? ds by dt, right? You use this. So based on my equation that says velocity is the function of time. Look, we use this to find velocity the function of time. We use the equation that says what? A dt is equal, where acceleration is constant, so we use a dt. Let's use the exact formula, where is a equal to dv by dt. We'll not cross multiply first. Let's look at it one at a time. Because acceleration is constant, so if we want to relate velocity as a function of time, we'll use a equal to what? dv by dt. So if we cross multiply, we'll have a dt is equal to what? dv, right? So we want to make v the subject because we want to represent v as a function of time, meaning that v will be represented as the dependent variable and now t represented as the independent variable. So in order to find v, we have to get rid of the variable of integration, which is what? D. So to get rid of the variable integration of d, it will have to integrate based on definite integral. So we integrate t on interval from 0 to t, because the initial value of t is 0 and the final value of t is just what? T, because the actual function here is what? dt. Again, we integrate this from what? V naught to what? V. So integrate the derivative from initial velocity to that of the final velocity, where A is what? Constant. So we say AC. So we factor AC, we have AC, a constant acceleration, will be the integral from 0 to t of what? dt is equal to the integral from v naught to v of what? dv. So if we integrate e dt, we'll have t, an integral of what? From 0 to t of a c, right? Again, if we integrate this, we'll have v on the integral of what? V naught to v. So when we're doing related to mathematics, we said that it will have a definite integral. After deriving, the definite integral says that it will have the integral from a to b of f of x dx. It means that will be equal to what? Capital F over b minus a. But the capital F is stands for the EDF, it stands for the integral after integrating. And it's already as well b minus a. So the upper boundary minus the lower boundary. So the upper boundary for this is what? T, the lower boundary here is what? 0. So we have AC on this side by t minus 0 is equal to the upper boundary here is V and the lower boundary here is what? V naught. So we have V minus V naught. So if we cross multiply, we'll have ACT. The acceleration is constant, so ACT is equal to what? V minus what? V naught. So we send V naught across, meaning that V will be equal to what? V naught plus ACT. So for this, it means that velocity is a function of what? Time, where acceleration is constant. And look at our second value, our second. So this is where velocity is the function of what? Time. So look at the next one where we realize that we're using this formula to derive all our functions where acceleration is constant. And look at our second. Our second one says we want to relate position as a function of what? Velocity. We want to relate what? Position as a function of velocity. If we want to relate position as a function of velocity, meaning that we have s of v, right? Where s is the dependent variable and v will be the independent variable. So if we want to find the position as a function of velocity where acceleration is constant, we'll use our last equation that says a ds is equal to what? V dv. Remember, a is what? Constant, so called what? AC. Right? We want to relate position as a function of our velocity. So we have to find the value of s. So in order to find the value of s, we have to get rid of the variable integration, which is what? S. So in order to get rid of the variable integration of d, we have to integrate. So integrate this guy for the interval because this guy is position, right? So the initial position is what? S naught. And the final position is what? S. Again, we integrate this guy from what? Initial velocity of v naught to v. If we factor AC, we'll have AC, constant acceleration, will be the integral from S naught to S of ds. Is equal to the integral from v naught to v of dvv, right? So we integrate this, the integral sign will cancel our d, so we left with s. So we have a constant acceleration s, the interval of s naught to s equal to. We integrate this, we'll have a v squared over 2, where we apply power rule. But integral power rule says that if you have the integral of x raised to n dx, will be equal to s raised to n plus 1, all divided by n plus 1 plus c. So add 1 to the power, we'll have 1 plus 1, we'll have 2, all divided by 2. on the interval from V0 to V. Again, when we say our boundary value idea, what we say, we have the integral from from A to B of f or x dx will be equal to f or b minus what? A. So do they say idea? So here is what? The upper boundary with x minus the lower boundary with what? S now. So we have AC multiplied by S minus S now is equal to, we'll do the same to this. We'll have V square minus V0 square all divided by 2. So if we cross multiply, we'll have 2AC minus by S minus S0 is equal to V square minus V0 square, right? So if we send this across, say we send V0 across, right? V0 is negative, so we send V0 across, we'll have V square will be equal to V0 square plus 2AC minus S minus. So it means this guy reason why velocity has a function of our position. So velocity in the case is the function of position, where we have V square equal to V0 square plus 2AC S minus what? S now. Let's look at our last function where we have position has a function of time. Look at our next function called position has a function of time. The position as a function of time, we'll use our first equation again, where we say V will be equal to ds by dt. So if we cross multiply, we'll have V of dt is equal to ds. Remember, where we have acceleration, velocity as a function of time, right? We say if velocity is a function of time, meaning that we'll get what? V0 plus ACT. Parenthesis by dt is equal to ds. Because we say if velocity is a function of time, if V will be equal to V0 plus ACT. We just did derivation, right? So again, you want to find position, because say position as a function of time. So what we do, we integrate this guy from S0 to S, right? Again, we integrate this guy from 0 to t. So if we integrate this, because this is a constant, right? A constant to t. But the verb integration is t. So it means this is a constant. So if we integrate this, we'll have V0 of t on the interval from 0 to t, plus if we integrate this, we'll have AC over t squared over 2 on the interval 0 to 2. We want to focus on the function here, right? Our function here is t. In the verbal integration here is t, right? So if we integrate this, we apply our power rule analysis. What we say, we have x raised to n or b equal to x raised to n plus 1 or divided by n plus 1 plus c is equal to. If we integrate this guy, we have s on the interval from s0 to s. So now we went to our substitution, right? This and this, we'll have v no parenthesis by t minus 0. Again, our same analysis we did first, plus AC parenthesis by t square minus 0 square all divided by 2 is equal to s minus s0. So we will get V0 of t, because t minus 0 is t. So this and this will give V0 of t plus multiply, we have AC all divided by 2 is equal to s minus s0. So we send this negative across, we'll have s to be equal to s0 plus V0 t, right? Because this count is the s0. This V0 of t plus 1 over 2 constant acceleration over t squared. So here we relate position as the function of time. So before going, let us climax our entire formula. So it says that if we have an instantaneous or linear motion or continuous motion, meaning that the velocity will be equal to what? The derivative of the position divided by the derivative of the time, right? And the acceleration equal to the derivative of the velocity divided by the derivative of the time. And our acceleration will be equal to d squared t squared x or dt squared. The acceleration will be equal to v dv or dx, which is a dx equal to what? V dv. So basically, once you got this, always, most of the time, if you want to find the acceleration, you always be what? Differentiating most of the time. If you want to find velocity, you either what? Integrate or differentiate. And find the velocity for this case, you will differentiate, right? So find the velocity for this case, you have to integrate because the value of v is d. That integrate. But most of the time, you want to find acceleration, you always be differentiate. So again, we say if acceleration is constant, when acceleration is constant, we can relate our velocity as a function of time. So we say a velocity is a function of time. We say that the formula will be v will be equal to what? V naught plus ACT, right? Where acceleration is constant. Again, we say that we can relate our velocity as a function of position, right? Or position is a function of velocity. So velocity is a function of position. Our equation was we have v squared is equal to v naught squared plus 2ac, right? And it will be s minus s naught, right? Again, we say we have our position. The position is a function of time. Then our equation will be what? S is equal to what? S naught plus V naught T plus half AC T squared. So again, we say if we have a continuous instantaneous motion, meaning that the value of velocity will be equal to the derivative of the position with respect of time, and the acceleration will be the derivative of velocity with respect to time, and our acceleration is the second derivative of the position with respect to time. And also say we have ADS equal to V dv, what we relate acceleration, velocity, and that of position. So again, we went to if acceleration is constant, then we can relate a velocity is a function of time. So if velocity is a function of time, means v will be equal to v naught plus ACT. If the velocity is a function of position, meaning that v squared will be equal to v naught plus 2ac minus will be s minus s naught. Then if position is a function of time, then s will be equal to s naught plus v naught t plus half ACT squared. Thanks for watching. Please don't forget to share, like, and comment. See you in our calculation video.